Swayam Prabha. Digital India. Educated India.
Okay, the reason why this is happening is this is a material called, when I coupled it and I heated it, it straightened. It's the metal with the memory. It's called shape memory alloy. Shape memory material. The shape memory material, whatever shape that it is in, when it is heated, it will go back to a shape that it was programmed to. For example, when she did this, there is a particular shape to it. I'll just show you. This is the shape, sort of one circle that you can see over here, right? When I straighten it, and then apply heat, it will memorize that particular shape that it had earlier, and it will go back to that particular shape. It will go back to that particular shape. Again, I'll do it. When I heat it, it goes back to its particular shape. And therefore, the name shape memory alloy. Okay. So, does it have, intelligence? Then it is made such a way that it, when you crumble it
in a certain way.
Yeah.
When you're eating it, you're giving enough energy for it to come back to its original position.
You just mention it again. When you are, yeah, go ahead.
Yeah, so
Oh.
so when you're crumbling material, you're actually changing the shape and you're bringing it to an uncomfortable position.
Uncomfortable position.
Yeah, it might be
Okay.
uncomfortable. When you're heating it, you're giving it energy, so it could come back to its
But
original.
every material should do the same, no?
No, it is uncomfortable. It wants to come back to its
Yeah,
original.
correct. Every material should have the same problem, no? I'm uncomfortable in the hostel. I want to go back home.
So when you heat it, the arrangement of molecules in the metal changes to a particular way, and then it stays in that. So
Yeah,
after
you're right.
cooling down,
You're right. There is a change in the arrangement.
yeah,
There is a change in the arrangement. Definitely, you're right.
The changes in such a way that it's better in the position that it's kept in at that temperature.
Okay.
But when you decrease the temperature and change the shape, it remains in that shape for that particular time, and when you heat it back, it goes to that other structure and becomes.
Mentioned it, when we heat it up, it becomes excited and wants to go to its most
See, every
stable.
material will do the same thing, no?
It is
How is it different? That's the question, correct? What is the shape memory, correct?
So like how the Pepsi can, when you just give a little push, it went back to its original.
Correct. See, that's what you can definitely understand through bistability. But how is it that it is occurring that way? That's the question. Stronger in a certain position, okay. Stable in a certain position.
So it didn't reach its elastic limit yet.
It didn't, no, it reached its elastic limit because you crumpled it, no. Yeah, go ahead. Yeah,
Sir, the metal when you bend it
for the first time he is talking.
No, sir. When you bend the metal, one side of it is getting compressed. What if the metal is like remains compressed? When you heat it that part expands,
No.
so it bends back.
Yeah, but that you're talking about thermal expansion?
I guess yes.
Yeah, but thermal expansion is very, very small. The reason why you have bimetallic strip is so that when you combine two materials with different thermal expansion coefficients, one of them wants to expand more, the other does not want to expand more, and therefore what happens? The fight gives a bending action. Very simple, no? I don't want to move. This says, oh, move, and then they accommodate and say, okay, this is the position. All right? That's the key way by which bimetallic strip is used, so that you can get a visible deformation that can be used in where? RHE. Rheostats, right? It is also used in places where you want to put on the fire extinguishing system. When there is higher temperature, it will switch. It's like a switch, correct? Yeah, if fire extinguishing, so on. But here it's very different. It's very different, correct? The difference is, some of you are right, it is bistable as a fuse. You can use it as a fuse. Circuit breaker, you are talking about circuit breaker. Yeah, it is possible to use it as a circuit breaker in a reversible way, right? There are so many applications. And I just want to complete that before 4 o'clock. Is that okay? Only that material. Shall I? Okay. So you need to switch to the other. You will do it? Sorry, I am taking a long time in explaining this, but before he shows everything, why does ice become water? Latent heat, it is heated, etc., etc. When it is heated, what happens to it? Okay. But why does it happen only at 0 degrees centigrade? Nature, what nature?
It's ready to give away.
You said no, bistable and all those. Can you tell me? At a temperature above 0 degrees, at a temperature above 0 degrees, fill in the blanks. What is more stable? Water in its fluid form is stable above 0 degrees. Below 0 degrees? The phase called solid is more stable, right? Stable, solid, stable, liquid, and the transition we call as what transition? Phase transition. So it exhibits a solid phase and a liquid phase and gaseous phase, correct? And each one of them will have a single temperature or a very small range of temperature where it shifts from one phase to the other, and we call that as phase transition. It's exactly the same thing that happens over here. It is the only difference is ice is not becoming water, solid is not becoming liquid, but solid is becoming another solid. Solid becoming another solid? Does it make sense?
The shape.
No? Huh?
Is it reacting?
Is it?
React.
Is it reacting? No, no reaction. No reaction.
Shape interaction. Shape change.
What shape?
First, it's the interaction.
What shape changes?
The shape.
Huh? Arrangement of the atoms. Very good. Arrangement of the atoms. From one arrangement of the atoms, it becomes another arrangement of the atoms. Alright? I am going to explain in a very, very simple manner so that you understand. Okay? Two phases. Definitely. Correct? I have to have two phases. One phase, as far as water was concerned, it was ice or solid phase and liquid phase. Correct? Where is the eraser? Yeah. Now, the way in which I can now explain to you is like this. Let's say, I am going to just use a caricature in order to explain to you. Let's say this is the typical unit cell of the crystalline material that I have, which is the shape memory alloy. Okay. When it is at one temperature, it is like this. In a very stable way. At a different temperature, it is like this. So what, sir? Why would it exhibit the shape memory and all those? Correct? Yeah? The beauty actually lies in, let's say this is the high temperature, T high. Okay? And this is T low. Okay? When I take this material and change it to this material, it will become something like this. Or will it become like this? Which one? This one or this one? Both. Any one of them? Any one of them? Yes or no? Supposing I heat it back, both the configurations will result in the same thing. So we call this as a parent phase. But this looks like a humanities professor talking, correct? So we'll make it a little bit more chemistry or scientific. So we call this a symmetric phase. This one we'll say asymmetric or not so symmetric. The difference is it exhibits symmetry. Whether I put it this way or that way, it doesn't matter. It has symmetry about this, symmetry about this, symmetry about this. Symmetry is lost over here, right? But the gain is it can form this as well as this in its stable state. Got it? It's clear now? I'm going to explain one more point here. Supposing I take this and push it like this, shear it like this, will I get this? Yes, no, right? If I shear it like this, I'll get this. If I shear it back, I'll get this. There's only two of them. Think of this parent. Think of this parent is like a pig. Sorry, I'm just using pig because pig lays a lot of piglets, right? Each one is a child, correct? Now, from a single parent, so many children are possible. Can one of them become the other by sharing? The answer is yes. Correct? So, when I take this, this is in a form that is here, low temperature. At the low temperature, if I ask what crystalline structure is there, it can be this crystalline structure or this crystalline structure, or if I bend it, it may go from this crystalline structure to that crystalline structure. Clear now? But when I heat it, it has to go back to this state, which is a symmetric state, which means whatever was the shape over here, I get it back. Here, by sharing back and forth whatever, I can crumble it and it will stay crumbled because all these are different faces put together, an ensemble of all the faces. Yes, sir. Aditi. By just looking at the geometry, no? You look at this symmetry and this symmetry. Is this less symmetry compared to this? Yes? Okay. Yeah, symmetric meaning what are the planes about which I can see the symmetry. Yeah.
No, but the coil thing that did not look so symmetrical.
Which one?
The coil.
Yeah, coil is made, this is made out of this material. Every molecule is arranged in such a way that it is either in this crystalline form or in this crystalline form. Right now it is in the low temperature. So what's crystalline form? I can stretch it, I can compress it, all that I can do. Correct? When I heat it, what will happen? It will come back to the shape that it had earlier. And therefore, shape is remembered over here, shape memory. Beautiful, no? The advantage is because it is from a solid phase to a solid phase. Yeah. Yeah, so different materials are possible. That I can have something like this. Tell me one more symmetric face, symmetric shape. Circle, orthorhombic, cubic. Yeah, there are so many shapes that are possible to get as far as symmetric is concerned. And from symmetric phase, I can always obtain not so symmetric by sharing. Right? I shear this, I can get this. Correct? So, I can get this, and this is a stable state at low temperature. Bistable. But here its stability is with respect to what? Temperature. Not like this where it is dependent on the force. Correct. This was because of the force. This is because of temperature. So, there is a temperature that divides these two, and this temperature can be called as phase transition temperature. Simple, no? Right? And therefore, now I have the strength of creating any shape. Yes or no? Any shape, right? So, let us see one shape like that. And in fact, you can you make it bigger? 5 more minutes I need to complete it. Close. Yeah. Okay. I'll come back to all this later. Oh God. Okay. Okay. This is what we did, no? So it remembers the shape. If it remembers the shape, suddenly somebody thought, okay, if I change water to steam and back again, which has to do with change in volume, I can do something. We are living in a world who took the advantage of that. I'll repeat it once more. The story goes as the fellow thought that if water turns to steam and there is a change in volume, I can now advantageously use it to do work. Steam engine, correct? Right? Steam engine, yeah? How is steam engine working? Going from one phase to the other, right? Yeah, correct? Phase change was involved. So can I not use that? Yeah. So what I will do is I'll take this spring. Right? Right now it is in what state? Low temperature. Right? I can stretch it. Nothing happens. Correct? When I heat it back, it should shrink. I will not let it shrink. What will happen? I will not let it shrink. You want to go back home, I will not let you go back home. What will happen? It will apply stress or force, correct? Let's watch that, okay? Yeah. So what I will do is, where is the, now, I'm going to hold it like this. Is it possible to do it this side so that they can see it? Is it possible? Can you get the heating stuff over here? I'm going to put a weight so that it has to pull the weight in order to go back. How about that? Where is the weight? Here. I'm going to hang the weight. Not let it go back. Shall we put some weight? We'll put some weight. Okay. Shall we put some weight? We have done that? Yeah? Is it hot? Okay. Are you able to see? No, they will not be able to see. Yeah. You're able to see, no? You're blowing hot air on me. Yes, I'm your advisor, but not this way. Hey, look at that, huh? Wow. Give it a hand here. But I'm not satisfied. Okay, yeah, I can now get it to work for me. When I cool it, what will happen? Okay. Not enough. I want to add more weight. Shall I? Huh? Not enough. Some more weight. This one. Make it work hard here. Huh? Do you think it will stand? Okay. Here. Oh my God. Look at that fellow, huh? He needs more applause. Where did it go? It has disappeared. Yeah, see, I got it to work too much, no? So it disappeared. See, we were able to get very thin people to break the rod, correct? Very small spring, can't find it, huh? That's it. No salary for you. No, it fell down, that is sure. No, I'm telling myself, no salary for myself. Okay. So, one thing that you can see is that it has, where is that? Yeah, that it has the capacity to lift, and I know why, because I'm changing from one phase to the other. I want to change from a phase which is not so symmetric to a symmetric phase. That symmetrizing makes it. Now, why is it that it is always at the higher temperature that you see symmetry? So, for example, I am going to ask you this question. It's a tough question. Which is more symmetric, water or ice? Wrong. Do you know water is more symmetric compared to ice? And steam is more symmetric compared to water. Right? We'll discuss that. But the thing is, it wants to go to a symmetric shape, and therefore it is okay to lift the weight, right? So we can use it as an actuator, right? And therefore I can design ways by which it is possible for me to make it a muzzle, correct? Right? People have started to use in various applications. One of the uses is by this actuation, okay? But this is not all. There is another property that it exhibits, but time is short, so we will discuss it later. Any questions?
Sir,
How do we design such a material? So I am just going to quickly go through that. I am purposely showing this. Heating is shrinking and cooling is expanding, okay? So you can make a shape, you can program a shape. 2 more minutes, I will just show you how to program, okay? And then I can get it back. I now stretch it. I take it to hot water. I now dip it. What will happen? It will remember that shape, right? And I love that material. Okay, so there's a lot more. I'll stop here, but probably we can meet once more later after I return to give you a little bit more details of such materials. Okay, this is one of many materials. Dharmi works on materials which are magnetic materials, magnetically responding materials. Hari works in this material which is shape memory alloy. Now, we'll do one more exercise and stop. Okay, come. I need 2 pairs of pliers. One is here, the other is okay. Let's take a wire, one of the shape memory wires. Yeah, this one, come. See, I am taking a wire, I am now going to program it. Just like you saw 2 different, one was 5, the other was loud, right? So I am going to make a simple one. How about, shall I make a knot? Oh, can you change the slide? Here. This is good. I'm going to make a knot, okay? And I'm going to program this knot. Shall I? Yeah? The way I program this is, I take it to a temperature where it is like a molten state. Remember that, okay? It is not going to melt, but you will see something that is close to it. Where is the lighter? Gas lighter is fine. Yeah. I'm now heating it. Just watch it. Just hold it tight. What's happening now? It's becoming red hot. Yeah? It's getting smaller, but it is red hot now. Huh? Now I cool it. It went through a molten state and now it's ready, programmed to be becoming a circle at that particular location. Shall we see if it is happening? This is a freezer. This is a freezer. Yeah, now I can touch it. I'm going to remove this now. Right now it's in what state? Low temperature state. I can now make it disappear. Right? No more I can see it. When I heat it, what will happen? Yeah, now you know what will happen, correct? Hold it in such a way that, yeah, bring it this side, yeah. Look at that, huh? Yeah, correct? Almost. If I do it for say 15 minutes at red hot state, it will remain as it is. I have now programmed it. Any shape, it doesn't matter. Why? Because basically I have programmed it to bring it to this shape. Right? At this shape, at this state, I program the shape, it will remain in that shape, and therefore it's called shape memory alloy. Clear? I'll stop here, else Professor Suresh will kill me. Yeah? Any questions? Other than, yeah. We'll precisely stop at 410. Okay? Yeah.
So you had said water is more symmetric than solid, like that. Steam is more symmetric than water, like that. You had said, right? What do you? I mean, how do you define symmetry for like undefinite?
Wonderful question. It has to do with order. So we introduce an order, which has more order, which has less order. That defines symmetry.
No, by order, what do you mean?
It's a separate subject that I have to talk to you about. 2 minutes may not be enough, but an ordered structure is usually less symmetric than a material with an order where there is a lot of change that is possible. Entropically, you can easily show that order and entropy are connected to each other. Entropy and temperature are connected to each other. And symmetry is also connected the same way. I know I have not answered you fully because for want of time, but we will definitely discuss in case there is a possibility. That's all. No other question? How can we cut water? Very simple. All you have to do is bring it to ice form, cut it over. Yeah, but you can cut also with a very, very high rate of strain, right? This is actually a fluid. This is actually a fluid, no? Yesterday I showed you, yesterday or day before, right? It's a fluid, but at a very high strain rate, it is breaking. Oh, what is this? Breaking is that of a solid, no? I'll stop here for want of time. Now, as far as the project is concerned, you can either do on smart materials or magnetic materials. I'm sorry, shape memory alloys or magnetic materials, correct? Yeah. So, both of them are here. They can answer you whenever you need a doubt to be cleared.
Sir, what is the wire made up of?
It's made up of two metals together. In this case, it is nickel and titanium together. Both are FCC materials. The two combined to form an alloy called nickel titanium.
which other combinations show the same property?
There are umpteen number of them. I have a slide. There are about 20-25 combinations that we have. Okay, so depending on what the need is, we choose the material appropriately. Name. Sahana. He will be very happy because you're standing and asking.
Sir, how does the freezer work?
Freezer work. Oh, okay.
Not the
Completely
actual
different
fridge,
question.
but
Okay.
that
Actually, good question. So you have water and you are blowing, correct? We form sweat because we want to cool ourselves naturally. Why? One single phrase. Huh? Latent heat. It can be latent heat, which is one is giving out heat, which is called exothermic. Depending on whether it is exothermic, every explosion is and give me an example for endothermic. Ice melting and so on, right? So now you are able to understand how I can absorb heat and release heat, correct? The freezer is a particular liquid which turns into vapor, transitioning through a latent heat, right? Simple. I don't know the name of this, but it's called. No. What is the content of this? It's written over there. Anyway, we'll see. If no more questions, I'll stop here because we need to leave. If you need me to give some more idea of smart materials, I'll come back later. But I'll be back only by around 15th of May. At that time, if you still have the interest, I'll show you. Okay? Thank you.